So it's pleasure for me to start the second morning session of this conference. And the first speaker is Stefan Ivkovic from Serbian Academy of Science. The title is Disjoint Dynamical Properties of Wedge Operators. So please.
Thank you very much. And I would like to thank organizers for giving opportunity to present this material. Yes, let me first fix some notation. If you have capital N greater or equal to 2, and you choose a finite sequence of bounded linear operators acting on a separable Banach space, then this finite sequence is called disjoint hypercyclic, or simply D hypercyclic, if there exists an element X such that this set contains n tuples of this form, if this set is dense in X to the power n. And in that case, the element X is called a D hypercyclic vector. And then if the set of all D hypercyclic vectors for this sequence of operators, finite sequence of operators, is dense in X, then we say that these operators T1, T2 up to Tn are densely D hypercyclic. So you can have one D hypercyclic vector, but it could happen that the set of all these hypercyclic vectors is dense in the whole space X, and in that case, this finite sequence of operators is densely D hypercyclic. This is the concept which we will mainly be interested in the rest of this talk. However, this concept works only for separable Banach spaces. On more general topological vector spaces, we have another notion which we call disjoint topologically transitivity. And this simply means that for any non-empty open subsets U, V1 up to Vn of X, there should exist a natural number n such that this intersection is non-empty. It turns out that in the case of separable Banach spaces, these two notions are equivalent. However, this notion regarding topological transitivity also works for general topological vector spaces. Now we shall speak about a criterion which ensures a densely D hypercyclicity. And this is called D hypercyclicity criterion. And what is that? If you have a strictly increasing sequence of positive integers, then we say that this sequence of operators satisfy D hypercyclicity criterion with respect to this sequence of integers whenever there exists some dense subsets x0, x1 up to xn of x, and the mappings SLK from XL into X, where L is between 1 and n, and K is a natural number, such that this sequence of operators converges to 0 pointwise on X0. These sequences converge pointwise to 0 on XL for each L, and also this convergence hold pointwise on XL for L between 1 and n. And here delta IL simply means that it is 0 when I is distinct from L and 1 when I is equal to L. In our situation, we will actually deal with invertible mapping, so this LK will simply be the inverses. But this is a general statement of this D hypercyclicity criterion. And of course, if this T1 up to Tn satisfy the hypercyclicity criterion, we say if there exists such sequence Nk for which this holds. And then I want to say that actually this D hypercyclicity criterion is stronger than the property of being densely disjoint hypercyclic. So it is actually just a sufficient criterion to test whether such sequence is indeed disjoint, densely disjoint hypercyclic. And now we shall fix the notation for our talk. So in this talk, H is a separable Hilbert space, and we take an orthonormal basis which we will index over the integers. Later we shall see why I choose to index over integers and not over natural numbers, but it is the same. It is separable Hilbert space. For each m, we let Lm be the span from E of E minus m up to En, and then we let Pm be the orthogonal projection onto Lm. And as usual, BH is the set of all bounded linear operators. However, B0 of H will denote the set of all compact operators on H. And now we will consider a special kind of elementary operators which are called wedge operators. And what is this? If you take two operators U and W on H, then you can consider this operator which is given in this way here, multiplying on the left by W and on the right by U. And then we should notice that this is also a well-defined bounded linear operator on B0 of H. Because B0 of H is an ideal, so this image will stay in B0 of H. And now we have the first theorem. So we choose these operators W1 up to Wn, invertible bounded linear operators. And then we take a unitary operator U, which we require to satisfy a special condition. Namely, for each k, there should exist such constant nk, such that this relation hold for all n greater or equal to nk. This means that un of lk is orthogonal to lk. And then to simplify notation, the operators t, u, w, k, we will simply denote by tk. And then we also choose a finite sequence of natural numbers, which is supposed to be strictly increasing. And then with this setup, we have the following equivalent conditions. The set of all d hypercyclic vectors of this sequence is dense in B0 of H, or in other words, this sequence is densely disjoint hypercyclic in B0 of H. And then the equivalent condition is the following. For each m, there exist the sequences of operators in B0 of H, and a strictly increasing sequence of natural numbers, such that for each L between 1 and n, these limits should hold. And in addition, for each pair of distinct SL between 1 and n, this limit should hold. So these operators should actually approximate in the norm this Pm. Recall that Pm is the orthogonal projection onto Lm. So these operators should approximate this Pm, but in addition, these limits should hold. And then one can see that we can also turn around the whole situation. We can consider the operator which sends f to UFW, where W is invertible and U is unitary, satisfying the condition 5. And then we have the same equivalent condition, only in this case we turn around the order of multiplication in these limits. And then it follows that if the operators W satisfy these conditions here, then their adjoints would satisfy these conditions here. So it is not hard to see. And it follows that if you can construct examples satisfying these conditions here, then automatically by passing to the adjoints, you have also solved this other situation for this operator here. And then at the first look, it may seem that this condition on the unitary operator is a bit artificial, but fortunately not. There is a whole class of unitary operators satisfying this condition. And how can we construct them? Well, if you let alpha be a translation on Z, and you define U alpha of EJ be E alpha of J for all J in Z, so you defined its action on the orthonormal basis. And then since it sends unitary orthonormal basis into itself, then it is actually a unitary operator, but not only that, it satisfies the property 5. So now you see why it was useful to enumerate the orthonormal basis by the integers and not by positive numbers, because then we can construct these examples of unitary, easily construct the examples of unitary operators satisfying these conditions. So there is a whole class of these unitary operators. And now we have the main theorem, and we shall spend some time on this theorem. So we have three equivalent statements. The first one is that these operators satisfy the hypercyclicity criterion on B0 of H, where U tilde is now a unitary operator on H, satisfying the condition 5. So now it is a particular unitary operator which satisfies this condition. But let us look at the second statement. The second statement says that these operators satisfy the hypercyclicity criterion on B0 of H for every unitary operator U. So now we pass to a general situation. We no longer consider a particular class of these unitary operators, but every unitary operator U on H. And of course, these operators are, as I defined in the beginning, multiplying on the right by U and on the left by W and taking these powers R1 up to Rn. And now we have an efficient third statement is efficient tool to provide examples. And what does the third statement say? It says that the operators W1 to power R1 up to Wn up to power Rn, these operators satisfy the hypercyclicity criterion on H. So in fact, the main contribution with this theorem is the equivalence between the statement 2 and statement 3. So now you see that actually it is no longer important to consider this specially unitary operator satisfying this condition. We only needed them to pass to the implication 2 implies 3. Because what you do is then to prove that 2 implies 3, then you take this special unitary operator, and for this unitary operator, then you turn back to these conditions. You prove that if you have such unitary operator under consideration, then these conditions should hold. However, one can prove that these conditions are so strong that they are actually equivalent to the hypercyclicity criterion for these operators on H. On the other hand, if these operators satisfy the hypercyclicity criterion on H, then this condition is so strong that it ensures that also these operators satisfy the hypercyclicity criterion on B0 of H for every unitary operator U. So summarizing, actually this special class of unitary operators is not important in itself. It is just the middle step in the proof to prove actually the equivalence between these two statements. And why is this important? Because it is easy to construct examples for the statement 3, and then this will automatically produce examples for the statement 2. And another important thing is to say that actually it is not just true for B0 of H, but it is also true for the ideal of trace class operators, or in other words, nuclear operators, and also Hilbert-Schmidt operators, or more generally for every Schatten p-ideal on this separable Hilbert space H. And now I will give some examples. So the most elementary example is of this kind. You let R1 be a natural number, R2 be equal to R1, and then you simply define W1 and W2 on H in this way here by define its action on the orthonormal basis. And one can show that actually these conditions are satisfied. And this setup can be even more generalized by showing that every bilateral weighted shift on L2 of Z with certain properties will induce such operators here. But a more interesting example is the following one. So now we let H be a particular Hilbert space, simply be L2 of R. And then we let alpha be a translation. So alpha of t is t minus 1 for all t in R. And then we let a small w1 and small w2 be the functions, measurable functions, bounded measurable functions on R defined in this way here. Once again, we let R1 be a natural number and R2 be equal to R1. And then we let the big W1 and big W2 be the operators on H, so on this space here, be defined as weighted composition operators. What is this? Well, actually, they are defined in this way. So you take first composition with alpha, and then you multiply with double with j, small double with j, where j is 1 or 2. And then actually the operators of this kind will satisfy the hypercyclicity criterion on H, which will ensure that actually also these operators then satisfy the hypercyclicity criterion on B0 of H for every unitary operator U. And also this setup is can be more generalized in terms of these conditions on alpha and WL. And I shall end up my talk with application to the left and right multipliers. Because naturally...
4 minutes.
Yes, this is the last result, actually. So you can guess from this theorem here that actually, since we consider every unitary operator U, then naturally we can also consider identity operator, and then the situation reduces to left multipliers. And then we actually have that in this case, here L denotes the left multiplier by these operators. These left multipliers satisfy the hypercyclicity criterion on B0 of H if and only if these operators satisfy the hypercyclicity criterion on H. And once again, we can replace B0 of H by every Chatain P ideal. And then, as I said, we have examples of these operators which satisfy the hypercyclicity criterion on H, which automatically give us the densely disjoint hypercyclic left multipliers. And I would just like to summarize the talk that you can consider even more general topological spaces like BH equipped with a strong operator topology, and then these operators will be disjoint topologically transitive on this space for every unitary operator U, whenever these operators W satisfy the hypercyclicity criterion on H. And also we have some algebraic generalizations to arbitrary non-unital C-star algebras. This has recently been published in Philomath. However, the results of this talk can be published in Bulletin of the Iranian Mathematical Society in Springer. And this is actually what I wanted to say, more or less. Thank you for your attention.
Thank you. Thank you very much. But maybe could you show the list of references for a moment of possible questions? Just the list of references.
Oh, yes. Here are a lot of papers which I use for my paper. In particular, this paper is very important, which have been published in Journal of Operator Theory. However, my paper, I see that I forgot to put here, but I put in the abstract. So you can find in the abstract, it is the paper published in the Bulletin of the Iranian Mathematical Society. For the interested people, I can send them in the mail archive version and also the link to the published version of the paper.